Last episode, date on or after made one contract explicit. It does not order two arbitrary strings. It parses two ISO calendar dates, then asks whether the first is on or after the second. The longer operator name was an honest local repair. It told us something the surrounding JSON could not. These values belong to a particular semantic category.
Why not keep naming every operation that way? Date on or after, number greater than or equal, money greater than or equal, string before, and so on.
We could, but then every value category duplicates the same ideas. And every new category expands the operator vocabulary again. That repetition is pressure for a type system. Describe what values are, then let general operations state which types they accept. Do not pack a declaration into the field expression. Field date should remain a simple request for the field named date. Its type comes from the transaction source schema. That schema says date is a date. Amount is money, and status and customer are strings. At runtime, a row environment tells field date which value to return. During checking, a row type environment tells the same expression which type it returns. The raw JSON text for January 1st is still a string. Wrap it in the date constructor, and the expression now produces a date. A generic greater than or equal operation can say, give me two values of the same ordered type, and I return a Boolean. Here both operands are dates. The specialized operation can now be understood as a convenient surface form that expands into this checked core. Now let types rise through the same tree that values climbed last time. The schema gives source the type rows of transaction, where preserves that row type. Group by customer produces groups keyed by string. Sum consumes those groups and produces rows of aggregate. Each aggregate has customer and total. Sort preserves those rows, and take preserves them again. The root therefore has type rows of aggregate, without opening the transaction table. Where determines the row environment for its predicate. Field status is a string, and the literal complete is a string, so equality returns a Boolean. Field date is a date. The constructed cutoff is also a date, so ordered comparison returns a Boolean, and combines the two Booleans into one Boolean. That is exactly the condition shape where requires. Every connection has become a checkable claim. Remove the date constructor, and the cutoff becomes an ordinary string again. The left operand is a date, the right operand is a string. The generic comparison refuses to guess that one should be parsed as the other. Canonical ISO strings happen to have a useful lexical order, but that accident is not the contract we want the rest of the language to depend on. Here is the quieter bug we already encountered. After sum, the rows no longer have an amount field. They have customer and total. Asking sort to read amount is therefore ill-typed at that exact argument. Both mistakes stop here. With a path to the bad node and 0 rows red. Structural validation said these were expression trees. Type checking asks whether the expressions can mean what their operators promise.
No transaction moved, but something still walked the entire program. What should we call that process?
Another interpreter. The evaluator reads an expression in a value environment and produces a value. The checker reads the same expression in a type environment and produces a type or a localized error. Types are not decorative labels pasted onto the tree. They are a static meaning computed from it. We now have one program and already two interpretations. The tree can produce ranked rows, or it can produce a proof that its connections are admissible. Nothing says those are the only choices. The same narrow waist can support explanation. Cost estimation, compilation, provenance, and optimization. Next, we keep the tree fixed and change what a traversal means.